Okay, here's the last part of this second lecture, Part D, dealing with modeling with curves. And in this part, we're going to deal with polynomials. Previously, we looked at logs, which to me is the best way to model curve relationships, although you get some disagreement. I like the modeling with logs because it's pretty easy, takes practice, but it's pretty easy to model curve relationships with logs. With polynomials, you run into some problems that we'll see as we go along here. But a polynomial, rather than just a y-intercept and a slope times x, say horsepower, sticking with that example, that'd be a straight line. If you add a squared term, horsepower squared, then that allows one curve in your relationship, a parabola. If you add a cubed term, that allows for two curves in your relationship, two bends in a line, in other words. So now some people go crazy with this and they add fourth power, fifth power, sixth power. The more higher powered, higher ordered terms that you include allows you to better predict your data. It allows more curves to fit wherever the data may be, which has its good and bad points. A bad point is how can you explain to somebody what the eighth power term means? Now there are occasions where this can be helpful, but in general I try to avoid it and try to recommend that people avoid it. Because imagine sometimes you'll see someone with 10 points on a scatter plot and they will have 9 power terms, which allows them to curve their line through every single point on a graph. But what have you really accomplished when you do that? Okay, enough preaching. Let's get down to business. I'm going to go kind of backwards here. Rather than drawing a curve and asking you to find the formula, this can be pretty difficult for, say, polynomial equations or impossible. I'm going to work backwards slightly. I've asked our program here, a computer program, to tell us what the curve is, and we're going to draw them and then interpret them a little bit. I think that'll work better for us. So, for example, with a squared term, you're going to have a y-intercept, b0. You're going to have a linear term, b1, and you're going to have a squared term, something multiplied times a squared term, b2. And R has told us these three numbers: 47 minus 0.266 and 0.000576. And those are those numbers that'll go in that equation there. And of course we can fill those in, plug in a horsepower, and then calculate a prediction. Wouldn't be too tough to do. But I think let's graph it and see some problems with doing this, and then try to show you how you can interpret these. It's a little more difficult. And in order to do this, I'm going to use a program on my desktop here called Maple. Maple is just what we call a symbolic algebra program. Don't worry about that. It helps you graph things and do math. So I've just put in the equation here. Miles per gallon equals 47.14 minus 2.66 times horsepower plus 0.000576 times horsepower squared. I put in also the coefficients from a cubic equation. 69 is the y-intercept, minus 0.733 plus 0.0349 minus 0.000. That would be what's multiplied times the cubic term here in our equation. And so I put that in here, and this program's good at graphing, and we'll see a couple of the things that it can do. First, I want to plot the squared equation and see what it looks like. Now you see the classic parabola shape here. The y-intercept at about 47. If a car had 0 horsepower, 47 miles per gallon is what it would predict. Notice what's going on here. It goes down. It allows one bend. But look at the minimum. It's at about 220 horsepower. And then the miles per gallon starts going up. This is a problem because our data does not do that. our data goes to 300 horsepower. And even though it starts flattening out, it doesn't go back up again. And so I would caution people about using this equation for cars that have 300 horsepower. Certainly 400 you wouldn't want to use this equation for. So that's one disadvantage. Now let's look at the plot for the cubic. Again, remember, if you add a cube term, it allows two bends in your equation. So here we're starting off at around 70 y-intercept. And then you go down and you see one curve flatten out, and then you see a second curve. Now again, I wouldn't recommend using this for predicting 400 horsepower because you get negative numbers. That's one downside there. But you see what the second curve allows it to do. Rather than going back up around 300 horsepower, it allows it to remain relatively flat and then go down a little bit. So I think this would fit the data a little better. If we go back to the other document, let me show you. Here's a plot of these two relationships. The red here is the cubic. We see it go back up and then down. It fits these points pretty good. The blue is the parabola, going down and back up. And they're still fitting the data okay over here, but starting to leave reality at this point. Also over here, the blue doesn't do as good a job on these low horsepower, high miles per gallon cars. The red doesn't do a great job either, but it does okay. Now, so looking at the graph is important when you do modeling like this. Not a lot of people that I know actually do plots to see what does the shape actually do. How does it behave? Now, another thing is, how can we interpret, or is there a way to interpret the minus 0.266 and then this plus 0.000576? The only simplistic way is to say, well, the first negative says that as you start here from 47, you're going to go down. The second positive means eventually you're going to head back up as horsepower gets larger. Now with the cubic, you can get a general feel from looking at the numbers similarly. You start at 70. You're initially going to go down. Then you're going to go back up. Then you're going to go down again. And that's what we see in our equation down here. Down, kind of back up, then down again. A common way that people will try to interpret polynomial equations is by using a derivative. And I can't teach you what a derivative is here, but a derivative tells you a slope. Although the slope's not going to be constant. Let's look at this equation here. What if I took the derivative with respect to horsepower? I'm just going to get Maple to do it for me and kick it out. It's pretty easy to do, but I'm going to do, just call this 1 equals diff mpg hp, and that's just saying take the derivative. What this tells me is the slope of the relationship between horsepower and miles per gallon is equal to this. Now, it depends on what horsepower you plug in. If I plug in 100 horsepower, then what is that going to give me? Minus 0.266 plus 100 times this number. 100 times, move the decimal place twice. Minus 0.266 plus 0.1152. And you're going to end up with the slope minus 0.266 plus 0.1152. It tells me that the slope for a 100 horsepower car is going to be 0.1508. What does that mean? Well, what that means is if you're in the range of about a 100 horsepower car,